question pertains to the use of a single bonding jumper for multiple conduits, specifically 6 2-inch polyvinyl chloride conduits coming from a meter stack going to a common pull box, from which metal-clad cable feeds 6 different unit panels. The inquiry focuses on the interpretation of National Electrical Code Section 250.102, which addresses the use of a single common continuous equipment bonding jumper to bond 2 or more raceways or cables, where the bonding jumper is sized for the largest overcurrent device supplying the circuits therein. In this scenario, the largest overcurrent device is 125 amps. The proposal is to use a number 6 copper conductor in one of the polyvinyl chloride conduits to bond the box and the 6 metal-clad cables. The conductor lands on a bus bar, which is also jumped to the pull box, and the metal-clad cable ground wires also land on the bus bar. Arguments can be made both for and against this approach. Let's examine the arguments in favor of using a single bonding jumper. Firstly, code compliance. National Electrical Code Section 250.102 explicitly permits a single bonding jumper to bond multiple raceways or cables where it is sized for the largest overcurrent device. Secondly, simplified installation. This method reduces the number of bonding conductors, making installation more efficient and reducing the potential for errors. Thirdly, enhanced grounding. The larger bonding conductor provides a more robust path to ground, ensuring effective fault clearing and safety. Fourthly, cost savings. Using a single bonding conductor instead of multiple conductors saves on both materials and labor costs. Now, let's consider the arguments against using a single bonding jumper. Firstly, limited bonding path. While the bonding conductor is sized for the largest overcurrent device, it may not provide an adequate path for ground currents if the fault occurs in a different raceway or cable. Secondly, potential for induction heating. If the bonding conductor is installed in a close parallel path to the metal-clad cables, it could experience inductive heating due to the current flow in the metal-clad cables. Thirdly, inspector disapproval. The inspector may not approve this bonding method due to concerns about safety or code compliance. Fourthly, lack of redundancy. If the single bonding conductor fails, it could compromise the grounding of multiple raceways or cables. A deeper dive into the relevant National Electrical Code sections is warranted. National Electrical Code Section 250.102 allows a single common bonding jumper to bond 2 or more raceways or cables. The key is that the bonding jumper must be sized in accordance with Table 250.102 cone based on the largest overcurrent protective device for the circuit supplied by the raceways or cables. Table 250.102 cone dictates the minimum size of the equipment grounding conductors for grounding raceway and equipment. For a 125 amp overcurrent device, a number 6 copper conductor or a number 4 aluminum conductor is typically required. The conductor must be installed in a manner that provides a low impedance ground fault current path. This means avoiding long runs and sharp bends. The bonding jumper must terminate on a suitable grounding bus bar or terminal in the pull box. The metal-clad cable grounding conductors must also terminate on this bus bar. The pull box itself must be bonded to the grounding bus bar with a bonding jumper sized according to Table 250.102 cone. To address the concern about induction heating, it's important to understand the principles of electromagnetic induction. When alternating current flows through a conductor, it creates a magnetic field around the conductor. If another conductor is placed in close proximity to this magnetic field, a voltage can be induced in the second conductor, causing current to flow. This is the principle behind transformers. In the case of the single bonding jumper running parallel to the metal-clad cables, there is a potential for inductive heating if the bonding jumper is not properly installed. The amount of inductive heating depends on several factors, including the current flowing in the metal-clad cables, the distance between the metal-clad cables and the bonding jumper, the length of the parallel run, and the frequency of the current. To minimize inductive heating, the bonding jumper should be kept as far away as possible from the metal-clad cables. It should also be routed in a way that minimizes the length of the parallel run. Twisting the bonding jumper can also help to reduce induction. If the bonding jumper is installed in a metallic raceway, the raceway will help to shield the bonding jumper from the magnetic field. The concern about limited bonding path arises from the fact that if a ground fault occurs in one of the metal-clad cables, the fault current must flow through the single bonding jumper to return to the source. If the bonding jumper is not sized correctly, or if it is not properly installed, it may not be able to handle the fault current, which could lead to a voltage rise on the equipment grounding system. This could create a shock hazard. To mitigate this risk, the bonding jumper must be sized according to Table 250.102 Cohen. It must also be installed in a manner that provides a low impedance ground fault current path. All connections must be tight and corrosion-free. The metal-clad cable grounding conductors must be properly terminated on the grounding bus bar. If the inspector is not comfortable with the single bonding jumper approach, there are alternative methods that can be used. One option is to install a separate bonding jumper for each metal-clad cable. This will provide a redundant grounding path and will eliminate the concern about limited bonding path. Another option is to use a larger bonding jumper. This will increase the ampacity of the bonding jumper and will reduce the voltage rise on the equipment grounding system during a ground fault. It is important to consult with the local inspector to determine which bonding method is acceptable. The inspector has the final say in whether or not the installation complies with the National Electrical Code. In addition to the code requirements, it is also important to consider industry best practices when designing and installing grounding systems. The Institute of Electrical and Electronics Engineers provides guidance on grounding and bonding in its Standard 142. Recommended practice for grounding and bonding of commercial and industrial power systems, also known as the Green Book. This standard provides detailed information on grounding system design, installation, and testing. It is important to ensure that the grounding system is properly tested after it is installed. This will verify that the system is functioning correctly and that it meets the requirements of the National Electrical Code. Grounding system testing should be performed by a qualified electrical testing company. The testing company will use specialized equipment to measure the impedance of the grounding system and to verify that the bonding jumpers are properly installed. The test results will be documented in a report, which should be kept on file for future reference. The grounding system should be inspected periodically to ensure that it is still in good condition. The inspection should include a visual examination of all bonding jumpers and connections. Any damaged or corroded component should be replaced immediately. The grounding system should also be tested periodically to verify that it is still functioning correctly. The testing frequency will depend on the environment and the criticality of the equipment being grounded. In corrosive environments, the grounding system should be tested more frequently. The grounding system is an essential part of the electrical system. It is responsible for protecting people and equipment from electrical shock and fire hazards. It is important to design, install, and maintain the grounding system properly. The design of the grounding system should take into account the specific characteristics of the electrical system and the environment in which it is installed. The installation of the grounding system should be performed by qualified electricians. The grounding system should be inspected and tested periodically to ensure that it is still in good condition. The information provided here is intended for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer to ensure that the grounding system is properly designed and installed. The National Electrical Code is a complex and constantly evolving document. It is important to stay up to date on the latest code requirements. Continuing education courses are available for electricians and other electrical professionals. These courses can help to ensure that you are knowledgeable about the latest code requirements and best practices. The grounding system is a critical component of the electrical system. It is essential to design, install, and maintain the grounding system properly. By following the guidelines outlined here, you can help to ensure that the electrical system is safe and reliable. The use of a single bonding jumper for multiple conduits is a complex issue that requires careful consideration of the National Electrical Code requirements, industry best practices, and the specific characteristics of the electrical system. It is important to consult with a qualified electrical engineer and the local inspector to determine the best approach for your particular application. When evaluating the arguments for and against using a single bonding jumper, it is crucial to weigh the potential benefits against the potential risks. While cost savings and simplified installation are attractive advantages, the potential for limited bonding path and induction heating must be carefully considered. Final decisions should be based on a thorough assessment of all relevant factors, with the primary goal of ensuring the safety and reliability of the electrical system. Remember that the inspector's approval is essential, and their concerns should be addressed with clear explanations and supporting documentation. If necessary, alternative bonding methods should be explored to achieve compliance and ensure a safe installation. Ultimately, a collaborative approach involving the electrician, engineer, and inspector is the best way to arrive at a solution that meets all requirements and addresses all concerns. It is also important to consider the long-term maintenance and reliability of the grounding system. A single point of failure, such as a single bonding jumper, can have significant consequences if it fails. Therefore, redundancy should be considered whenever possible to enhance the overall resilience of the grounding system. Regular inspections and testing are essential to identify and address any potential problems before they lead to a failure. In conclusion, while the National Electrical Code permits the use of a single bonding jumper for multiple conduits under certain conditions, it is not a one-size-fits-all solution. A careful evaluation of the specific application, potential risks, and alternative methods is necessary to ensure a safe and reliable electrical installation. Consultation with qualified professionals and adherence to industry best practices are essential for achieving a successful outcome.